Dear students, after studying this module, you shall be able to know about gas chromatography, advantages of gas chromatography, principle and instrumentation required for gas chromatography, and finally the applications of this chromatography. Gas chromatography (GC) is probably the most utilized of all the chromatographic techniques. Since early 1950s, when the technique was first used for the separation of amino acids, gas chromatography now finds thousands of applications in virtually all spheres of chemistry and biochemistry. The technique is used in the separation and identification of constituents of the atmosphere, drugs, foodstuff, petrochemicals, pesticides, etc. Gas chromatography is similar to column chromatography, except that the gas is used as a mobile phase instead of a liquid. In gas liquid chromatography, which is GLC, the stationary phase is a thin layer of non-volatile liquid bound to a solid support. Separation takes place by the process of partition. On the other hand, gas solid chromatography GSC utilizes a solid adsorbent as a stationary phase and separation takes place by adsorption process. The gas liquid chromatography is more popular than gas solid chromatography and has relatively more applications. Gas liquid chromatography was developed by A.P.J. Martin in 1951 together with A.T. James. In 1952, Martin and Singe were awarded the Nobel Prize in Chemistry for their work on the development of partition chromatography. Advantages of gas chromatography. The main advantages of gas chromatography are the technique has good resolving power and even complex mixtures can be separated into constituents. It is sensitive technique with few milligram of sample being sufficient for analysis. It provides good precision and accuracy. The analysis can be completed in a very short span of time. The cost of instrument is relatively low with long lifespan. The technique is suitable for routine analysis as the operation of a gas chromatograph and related calculations do not require highly skilled operators. Gas chromatography is at present the most widely used and powerful tool available for separations. The major factors for this are the speed, good resolution and extreme sensitivity of the technique. For example, using this technique, it is possible to separate 10 isomers of heptane in less than 10 seconds. The detectors are available with the detection limits as low as 10 to the power of minus 12 to 10 to the power of minus 14 grams. Principle of gas chromatography. When gas or vapor comes in contact with the adsorbent, certain amount of it gets adsorbed on the solid surface. The phenomena takes place according to the well-known laws of Freundlich, that is x by m is equal to kc to the power of 1 by n, or Langmuir, which is x by m is equal to k1c plus k2c, where x is the mass of the gas or vapor absorbed in the mass m of the sorbent and c is the vapor concentration in the gas phase, and k, k1 and k2 are constants. Similarly, if the vapor or gas comes in contact with the liquid, a fixed quantity of a gas is dissolved in the liquid. The phenomena takes place according to the Henry's law of partition, that is x by m is equal to kc. Now both the phenomena are selective and there are different k values for the different vapor sorbent pairs. The principles of gas chromatography can be explained in the terms of following experiments. A gas that is flowing smoothly at the rate of 3 feet per minute down an empty tube that is 6 feet long takes 6 by 3, which is 2 minutes to flow from one end of the tube to the other. If such a tube were filled with the sand, the gas would flow through it more slowly. If the rate at which the gas flows in the sand filled tube is 2 feet per minute, it will take the gas 3 minutes to traverse the tube. The sand-filled tube in this example has some properties of a gas chromatography column. The gas is moving mobile phase and the sand is stationary phase. The gas emerges after it has passed through the column is called as eluent. In practice, the mobile phase should be relatively insoluble in stationary phase, otherwise the stationary phase becomes overloaded. Gas liquid chromatography. Gas liquid chromatography consists of a mobile gas phase and a stationary liquid phase which is coated on with either a solid matrix, diatomaceous earth or the wall of capillary tube. Typically, the stationary phase has sufficiently low vapor pressure in millimeters at column temperature so that it can be considered as non-volatile. The sample mixture in the gaseous form is run through the column along with the carrier gas. Separation can be achieved by the differences in the distribution ratios of the components of the mixture at different rates and with the different retention times. After elution, the sample apparatus can be detected by a suitable detector at the exit. Basically, all gas chromatographs, whether GLC or GSC, consist of 6 basic components. A carrier gas, which is an inert gas supplied at a high pressure and is passed to the instrument at a rapid and a reproducible flow rate. A sample injection system, the separation column, one or more detectors, thermostat chamber for the temperature regulation of the column and the detectors, and finally an amplification and a recorder system. The gas chromatographic separation is conceived out of the column made of glass, metal or Teflon. In this column, a sorbent is filled as stationary phase. The sorbents are packed in the variety of fine size graded powder, whereas the liquids are either coated as fine film on the column wall or first covered over an inert graded porous support such as fiber brick powder, followed by packing in the column. An inert gas as mobile phase flows continuously through the column. It is known as carrier gas and serves to transport the sample components through the column. The sample is introduced in the vapor form at the carrier gas entrance end of the column called as the injector port. Different constituents of the sample are adsorbed on the stationary phase to different extent depending upon their distribution coefficients. The portion of each constituent in the gas phase is swept along by the carrier gas. To maintain the K value, a portion of the sorbed amount will go into the sorbent at the next point in the column again. The desorption process goes on consecutively and endlessly. The entire band for each constituent moves further in the column, having the shape of more or less Gaussian distribution. It should be kept in mind that the gas is the driving force for the movement of zones through the column, and the solid for the GSC or liquid for GLC provides the selective retarding force. The detector can be regarded as a brain of the chromatograph and the column as its heart. The detail of the various components of the gas chromatographs are: firstly, the carrier gas. The carrier gas plays a vital role and varies as per applications. Carrier gas should be dry, free of oxygen and chemically inert. The most extensively used carrier gas are hydrogen, helium, nitrogen and air. Hydrogen has more advantage as carrier gas compared to the other gases, but is dangerous to use. Helium is second best but is expensive. Nitrogen is inexpensive but gives reduced sensitivity, and air is used only when the oxygen in the air is useful for the detection or separation. Helium is generally used because of its exceptional thermal conductivity, inertness, low density, and it allows the greater flow rates. Hydrogen has superior thermal conductivity and lower density, but has a disadvantage that it may react with the unsaturated compounds and explode. All carrier gases should fall between 99.995% to minus to 99.9995% purity range and contains low levels, even less than 0.5 ppm of oxygen and total hydrocarbons in the tank. The carrier gas contains a molecular sieve to remove water and other impurities. Traps are another option to remove traces of water and other contaminants. A two-step pressure regulation is required to minimize the pressure surges and to monitor the flow rate of the gas. A carrier gas is required in GC system to flow through the injector and push the gaseous constituents of the sample into the GC column, which leads to the detector. For selecting a carrier gas, following considerations should be taken into account. Firstly, the carrier gas should be inert, that is, in other words, it should not react with the sample, stationary phase or contacted hardware. Suitable for the detector employed and type of the sample analyzed. Readily accessible in the high purity and should be cheap. Best column performance consistent with the required speed of the analysis and does not cause the risk of fire or explosion hazards. Sample introduction system. The sample introduction system is very vital as a very small amount of the sample is injected into the column. The system must introduce a sample in reproducible manner and must vaporize it instantaneously so that the sample will enter the column as a single plug. Liquid samples are commonly introduced by hypodermic syringe through a self-sealing rubber septum to a small inlet chamber which may be heated to cause the flash evaporation. The temperature must not be so high that it decomposes the sample. The solid sample must be dissolved in a volatile liquids for introduction or may be introduced directly if it can be liquefied. Gas samples require special gas sampling valves for introduction into the carrier gas stream. The separation columns. Open tubular columns and packed columns. Open tubular columns, which are also called as the capillary columns, come in two basic forms. The first is wall coated open tubular column and the second is support coated open tubular column. W-cot columns are capillary tubes that have a thin layer of stationary phase coated along the column walls. In S-cot columns, the column walls are first coated with a thin layer about 30 micrometers thick of the adsorbent solid such as diatomaceous earth, a material which consists of a single-celled sea plant skeletons. The adsorbent solid is then treated with the liquid stationary phase. While S-cot columns are capable of holding a larger volume of the stationary phase than the W-cot column due to its larger sample capacity. W-cot columns have better column efficiencies. One of the most popular types of capillary column is the special W-cot column called as the fused silica wall coated open tubular column. The walls of the fused silica columns are drawn from purified silica containing minimal metal oxides. These columns are a lot thinner than the glass columns with the diameters as small as 0.1 mm and lengths up to 100 meters. To protect the column, a polyimide coating is applied to the outside of the tubing and bent into coils to fit inside the thermostated oven of the gas chromatography unit. FSWC columns are now replacing the older columns due to increased chemical inertness, greater column efficiency and smaller sampling size requirement. Packed columns are made of glass or metal tubing which is densely packed with the solid support like diatomaceous earth. Due to complexity of packing the tubing uniformly, these type of columns have larger diameter than the open tubular columns and have a limited range of length. As a result, packed columns can only achieve about 50% of efficiency of the comparable W-cot column. Furthermore, the diatomaceous earth packing is deactivated over time due to semi-permanent adsorption of the impurities with the column. In contrast, FSWC open tubular columns are manufactured to be virtually free of these adsorption problems. Different type of columns in their length, inner diameter, efficiency, sample size, pressure, speed, inertness have been depicted here in the table. Detection system. The detector is a device located at the end of the column which provides a quantitative measurement of the constituents of a mixture as they elute in the combination with carrier gas. In theory, any property of the gaseous mixture that is different from the carrier gas can be used as a detection method. These detection properties fall into two categories: bulk properties and the specific properties. Bulk properties, also known as the general properties, are properties that both the carrier gas and analyte possess, but to different degrees. Specific properties such as nitrogen phosphorus contents have only limited applications, but compensates for this by their increased sensitivity of the detector. Each detector has two main parts, which when used together serve as transducers to convert the detected property changes into the electrical signal that is recorded as chromatogram. The first part of the detector is the sensor, which is placed as close to the column exit as possible in order to optimize the detection. The second is the electronic equipment used to digitize the analog signals so that the computer may analyze the acquired chromatogram. The sooner the analog signal is converted into a digital signal, the greater signal to noise ratio becomes, as analog signals are easily susceptible to many types of interferences. Common type of gas chromatography detectors. Mass spectrometry detectors. Mass spectrometer (MS) detectors are most powerful of all gas chromatography detectors. In GC-MS system, the mass spectrometer scans the masses continuously throughout the separation. When sample exits the chromatography column, it is passed through a transfer line into the inlet of the mass spectrometer. The sample is then ionized and fragmented, typically by an electron impact ion source. During this process, the sample is bombarded by the energetic electrons which ionize the molecule by causing them to lose an electron due to the electrostatic repulsions. Further bombardment causes the ions to fragment. The ions are then passed into the mass analyzer where the ions are sorted according to the m by z value or mass to charge ratio. Most ions are only singly charged. Flame ionization detectors. Flame ionization detectors (FID) are most extensively used detectors. In a FID, the sample is aimed at an air hydrogen flame after exiting the column. At such a high temperature of air hydrogen flame, the sample undergoes pyrolysis or chemical disintegration. Pyrolyzed hydrocarbons release ions and electrons and that carry current. The high impedance pico ammeter measures this current to monitor the sample elution. Thermal conductivity detectors. Thermal conductivity detector (TCD) were the first detectors developed for the use with gas chromatography. The TCD works by measuring the change in carrier gas thermal conductivity caused by the presence of the sample, which has a different thermal conductivity from that of the carrier gas. Their design is relatively simple and consists of an electrically heated source that is maintained at a constant power. The source is usually a thin wire made of platinum or gold. The temperature of the source depends upon thermal conductivities of the surrounding gases. The resistance within the wire depends upon temperature, which is dependent upon the thermal conductivity of the gas. Electron capture detectors. Electron capture detectors (ECD) are highly selective detectors frequently used for detecting environmental samples. The device selectively detects organic compounds with moieties such as halogens, peroxides, quinones and nitro groups and gives little or no response for all the other compounds. Therefore, this method is best matched for application when trace quantities of chemicals such as pesticides are to be detected and other chromatographic methods are unfeasible. Atomic emission detectors (AED) are the latest embellishments to the gas chromatographers' arsenal. They are element selective detectors that utilize plasma, which is partially ionized gas, to atomize all the elements of the sample and excite their characteristic atomic emission spectra. There are three ways of generating the plasma: microwave induced plasma (MIP), inductively coupled plasma (ICP), or direct current plasma (DCP). MIP is most commonly employed form and is used with diode array to simultaneously monitor the atomic emission spectra of several elements. AED is an extremely powerful detector that has wide applicability. The different type of the detectors have been summarized here in the given table. Thermostated chambers for the temperature regulation of the column and detector. Column in a GC are contained in an oven, the temperature being specifically controlled electronically. The rate at which the sample passes through the column is directly proportional to the temperature of the column. Higher the column temperature, faster the sample moves through the column. However, faster the sample moves through the column, less it interacts with the stationary phase, leading to incomplete separation of the analytes. A method which maintains the column at the same temperature for the entire analysis is called as the isothermal mode. Most methods, however, increase the column temperature at a certain rate during the analysis. Programming of the initial temperature, rate of temperature increase, the temperature ramp, and the final temperature are called as temperature programming. A temperature programming allows the analyte that it elutes early in the analysis to separate adequately, while shortening the time it takes for the late eluting analytes to pass through the column. Amplification and recorder systems. These are the final components of the gas chromatographic instrumentation setup, which records the signals from the detector systems. They use certain electronic circuits to process and amplify these signals so as to display in an understandable graphical format, representing several peaks of the constituents of the sample in analysis. Application of GCMS. GCMS is a sophisticated separation technique that cannot be compared with the other modern analytical equipments, but can be complemented by mass spectrophotometer to achieve GCMS and mass. It has wide variety of application that caters to the academic research, quality control as well as industrial applications. Its concise, efficient automated system gives fast, reproducible and effective results that serve a key role in the advancement of science and technology. This resourceful analytical technique could be explored for the better prospects in future. It has established applications in various fields such as environmental monitoring, food, beverage, flavor and fragrance analysis, biological and pesticide detections, security and chemical warfare agent detection, chemistry and geochemical research, medicine and pharmaceutical applications, petrochemicals and hydrocarbon analysis, doping of drugs. Recent application of GC in the forensic sciences, including those in the forensic toxicology, which include alcohols and drugs in drivers, markers of the alcohol abuse, volatiles and anesthetics, carbon monoxide poisoning, after poisons, drug facilitated sexual harassment and drug profiling, and more general applications to criminalities in areas such as fire debris, car paints, explosive, toners, fibers, inks and finger mark analysis. Forensic and criminal cases such as analysis of ethanol in blood prohibition cases for the percent of ethanol in alcohol, analysis of drugs, mixture of for one or more components, chemical identification in an individual substance, etc. The gases most commonly encountered by the forensic chemists are carbon monoxide, carbon dioxide, light hydrocarbons, cyclopropane and ethers. Carbon monoxide and carbon dioxide are usually absorbed by the blood from the environment of a partial combustion. All these gases are analyzed using GC. With respect to the emerging role of forensic sciences for the arson investigation, a low cost and promising on-site detection method for the ignitable liquid is desirable. gas chromatography differential mobility spectrometer GCDMS was investigated as a tool for analysis for ignitable liquids and the fire debris. Flammables are the number one tools of the arsonist. Fortunately, evidence of their use is not completely destroyed even for the flammable material of high vapor pressure or when the environment has been elevated at the temperature for several hours. Types of materials to be expected include gasoline, paint thinner, charcoal lighter, turpentine and many more. None of these materials are single compounds but definite mixtures, and for this reason identification may be established by preparing a chromatogram. In addition to the applications mentioned in this paper, such materials as perfumes, coatings, plastics, oils, solvents and poisons readily lend themselves to the chromatographic analysis. To summarize, gas chromatography is probably the most utilized of all the chromatographic techniques. In gas liquid chromatography, the mobile phase is gas and the stationary phase is a thin layer of non-volatile liquid bound to solid support. Separation takes place by the process of partition. In GSC, it utilizes a solid adsorbent and a stationary phase, and the separation takes place by adsorption process. Gas chromatography is similar to the column chromatography except that the gas is used as a mobile phase instead of a liquid. Gas chromatography is at present the most widely used powerful tool available for separations. The instrumentation required for gas chromatography are a carrier gas, sample ejection system, separation column, detectors, thermostat chambers, amplification and the recorder system. Gas chromatography can be used in various fields like environmental monitoring, food, beverage, flavor and fragrance analysis, forensic and criminal cases, doping of drugs, medicines and pharmaceutical applications, security and chemical warfare agent detection, forensic applications such as the cases of arson, blood, alcohol, etc.